So let's discuss average rate of change in this particular video. And the average rate of change is a very general term that we can use for any function. Normally, if we're talking about a linear function, we would refer to its average rate of change as simply the slope. But what if we don't have just a line? What if we have something that looks like this? And in this particular graph, and it is the height as a function of age, so we can see a baby, and we can see this person, this man, growing to age 20. So let's read. If the graph of a function is not a straight line, the average rate of change between any 2 points is the slope of the line containing the 2 points. This line is called a secant line, and we can see this in this particular figure. This graph is the graph of a particular man's height in inches as a function of his age in years. 2 points on the graph are labeled. So we have one here at 13 years of age and one here at 18 years of age. So what I want to point out here is how the average rate of change changes as you progress through the domain. The secant line that connects these 2 points just gives you a snapshot of one slice of the domain. In this case, the slice of the domain from x equals 13 to x equals 18. So you can see what's happening here. Now, let's look at how they do the calculation. The man's average growth rate between ages 13 and 18 is the slope of the secant line containing those 2 points. Now, notice we're just finding the change in y over the change in x. So, of course, the y value is 76 minus 57, that's 19. And the x value is 18 and 13. 18 minus 13 is 5. Now, what this average rate of change tells us is within the snapshot of 13 years to 18 years, the man is growing about 3 4/5 inches per year. That's what the average rate of change tells us. Now, what I want to point out here is that the average rate of change is going to be different if we consider 1 year to 5 year. We can see that that secant line is going to be a little bit steeper. Also, what if we considered 16 years to 20 years? That secant line would almost be horizontal. So the average rate of change changes as you progress through the different slices of a function. So we're going to be looking at another function now, and that function is the cubic function. So here we've got investigating average rate of change given this particular function, f of x equals 1/2 x cubed. Now, the first thing I want to do is plot this graph. So if we're going to plot this graph and it's 1/2 x cubed, first of all, let's make a little table of values so we can see what's going on here. This is a cubic function. It will be a curve. So let's put in the most obvious one, which is 0, 0. Yes, this graph does go through 0, 0. If we put in 1, 1 cubed is 1, half of 1 is 1/2. That 1/2 up front is going to make this a little bit flatter in the middle. And then if we put in -1, we get -1/2 because -1 cubed is -1, -1 times 1/2 is -1/2. So back 1, down 1/2. If we put in 2, let's see, 2 cubed is 8, half of 8 is 4, over 2 up 4. If we put in a -2, we will get a -4. So basically, we got enough information here. We can graph this now. So we have this nice, smooth curve. Now what I want us to look at is 2 different slices, 2 different secant lines. So the first secant line that I want to draw in is going to be when x equals -1. We'll let that be x of 1, and then we'll let this be x of 2. So when x equals -1 and x equals +1. So here's that secant line. Here is that secant line, okay? So we can see that it is positive, and we can also see that this graph is forever increasing. Through the entirety of this graph, we have an increasing function. But what would that average rate of change be when x equals x sub 1 equals -1 and x sub 2 equals +1? So here we go. We're letting x sub 1 be -1 and x sub 2 be +1. So we're going to plug it into the formula here. So delta y over delta x, and we've already got these values, so all we have to do is plug them in from our table of values here. So f of x sub 1. So if x sub 1 is -1, here's x equals -1, y equals -1/2. So -1/2. And then here we are going to go over to +1. So minus +1. Let me get that right. So minus +1/2. So there we go. That's our f of x sub 1 minus f of x sub 2. That's kind of hard to say fast. To the bottom, x sub 1 minus x sub 2. So -1 minus 1. When we simplify here, we get -1/2 minus 1/2. That is -1. Over -1 minus 1, that's -2. So the average rate of change in this slice of the domain is simply 1/2. But let's compare that to what the average rate of change will be when we go from, let's say, 1 to 2. So now, different values, different secant line, much different average rate of change. So here we go. We got a new secant line, the yellow one, much steeper. So let's see, I think I'll fit that right down here. So now we're looking when x sub 1 equals 1 and x sub 2 equals 2. So delta y over delta x, so that's f of x sub 1 minus f of x sub 2 over x sub 1 minus x sub 2. So let's plug in those values. We've got them right over here in our XY chart. So when x sub 1 equals 1, we're at 1/2, minus when x sub 2 equals 2, we're at 4, over 1 minus 2. I'll move this way. So 1/2 minus 4 is, we'll put that over 1 times 2 times 2. That is 1/2 minus 8/2. That is -7/2 over -1. So if we have -7/2 over -1, that's equal to 7/2. So the average rate of change is substantially different in this slice of the domain. Much, much, much steeper. So the average rate of change, as I said, is a very general way for us to look at a function in its entirety at different slices of the domain as we go through the function. Clearly, the average rate of change will even be steeper if we considered the next point. If we were to plug in x equals 3, 3 squared is 9, and 3 cubed is 27, and half of 27 is 13.5. So that would be a point way off our graph. So the average rate of change changes as we go through the function depending on what we plug in for our x values.